Well, thank you very much, both for the very nice introduction and for inviting me to speak here. It's really a pleasure. So I'm going to speak to you about something kind of new we've been doing in the lab, which is hopefully related to all of your interests in multi-robot systems. I'll tell you a little bit about some of the other things that we do as well. But maybe just to start off, so I've been thinking a lot in general over recent years about where this whole area of robotics is going. So my primary interest has been in computer vision, and in particular simultaneous localization and mapping using vision. So how do we make intelligent devices that understand the spaces around them and eventually can do intelligent, useful things in the world, we hope. And of course there are some products and systems that are already out there, but where are we going with this technology? Where might we be in, let's say, 10 or 20 years? So let's imagine, and this is just an image I found on the internet somewhere, it doesn't represent any real concept that I know, but let's imagine something like a smart farm of the future in 10 or 20 years time. I'd expect there'd be various intelligent, autonomous devices involved in that, maybe drones, robots doing various things, sensor networks, maybe even people, with wearable or handheld systems of various kinds. How is all that stuff going to work together? How is it going to be interoperable? How are all these different devices maybe going to help each other, to know where they are, to know what everything's got to do? So for instance, you might have a set of robots whose goal is to go and water a whole field or something like that, and they've got to coordinate their actions in order to do that. So one obvious possible way that could happen is some kind of unified cloud service. So let's imagine the future of a maps type of service that might eventually be connected to all of these devices. All of them are kind of sharing information through some central server, and they're coming to, all of their instructions, their localization is being fed through that. So that is one possible vision. The question I'd really been interested in is there a viable alternative to that, which is not necessarily all controlled by a single kind of company or entity, can involve much more peer-to-peer type of communication and decision-making. So is there a viable decentralized alternative? So I'd expect these are the sorts of things that a lot of people in this room are very interested in. So in particular, what I've got interested in recent months is distributed localization. So I think a key problem in multi-robot systems is how do all the robots know where they are in the world? So in particular, without needing any kind of globally centralized system, is there a way to do it based on purely local computation and decentralized estimation? So, in particular, when we've got varied robots, heterogeneous systems, real complicated, noisy sensors and motions and all of those things. So I'm going to present you a new piece of work we've been doing, which we call Robot Web, which we think is a possible, very promising new solution to this problem. It's based on Gaussian belief propagation, and I'll explain a little later what that means, but I'm just going to give you a very quick flavor of it first. So just run a very quick demo here that I'm going to show you more of later. But this is visualizing a system where we've got a whole lot of robots in a space. So each of these is a little robot that drives around on the ground. And as it moves in the space, we would like to estimate its location. So let's just get an idea for how hard this is. So let me just do this. So if I just click this and run one step here. So what these red lines are showing is all of the measurements that all of these robots might have made of each other. So what we're assuming is these robots move around in a space. They all have some kind of odometry to estimate their local motion. And then they have a sensor which can make measurements of other robots. So if you like, the other robots are serving as landmarks for each robot. So it has some kind of range bearing type of measurement with noise of where the other robots are relative to its position. And on any particular step, these might be the measurements that are gathered. So every robot measures some of the robots that are nearby, for instance. How do we go from all these complicated measurements, which may be noisy, to actually solving in a good kind of global coordinate frame for the positions of all of these robots? So we've got a method that can do that. So if I just kind of run this, let me just change a couple of settings here that make it a bit faster. We are actually jointly solving here in a distributed way for the motions and positions of all of these robots. If I just turn off this factors thing. So in fact, for every robot here, we are visualizing both an estimated location and a ground truth location in our simulation here. And just to give you a quick idea of what would happen if we weren't doing that. So if I'll set the sensor range to 0, that means no robots will make any measurements. So if we just let them all run here blindly, so here they're navigating using only odometry, and you'll see that each one sort of splits into two. We see the ground truth estimate, the ground truth position and the estimated position gradually diverge from each other. So the robots are getting uncertain in their estimates. If we turn this measurements back on, and run again, we can see that they're able to kind of lock back onto their position estimates quite accurately. So I'll show you some more of that later and obviously explain how it works. But let's just go back to the slides. So I think before talking more about this robot web idea, I want to explain a bit more how I got interested in that, or how we came to these methods that actually lead us to a possible solution of that. So my main interest in research over the years has been in visual SLAM, so simultaneous localization and mapping. So how, and this is really about single devices mostly, how does a single robot or other device with a camera build a map of the space that it's in, which is good enough in particular to help it localize. So localize means where am I? And I've been working in this area ever since my PhD back in the 90s in the University of Oxford. And it's amazing to me that there are now systems and products you can actually buy that use this technology. So in fact, one of these at least, this is the Dyson 360i. I'll just quickly show you a video. I was personally involved in this project working with Dyson to design a visual SLAM system. So this is a robot that has an omnidirectional camera. It has one button kind of operation just to make it go. And then it will automatically drive around your home, and it will use its camera to build a map of natural landmarks in your home that it can use as a set of beacons, basically. So we didn't want to have to put any sort of infrastructure up in this room, so there's no kind of markers or anything. It just uses naturally occurring points in the scene. So things like the corner of a picture on the wall or something is a point that it can repeatedly find. So as the robot is driving around, it's tracking these landmarks and essentially building a 3D map of where the landmarks are. The landmarks here are arbitrary points, but what we really care about is where is the robot? Because if we've got a good enough landmark map, we can jointly estimate the position of the landmarks and the position of the robot. And if we know the position of the robot, we can then clean in a systematic way. So if you saw early robot vacuum cleaners, they pretty much bounced randomly around a room over a long period of time and hoped to find their way into all the corners. This robot and other similar ones, because they're doing proper localization, they can clean in a really systematic way. So that hopefully immediately helps you to understand why localization is so important. So there are other quite different sorts of products that have a very similar kind of technology for vision-based localization via landmarks. So some of these are certainly what we would think of as robots. So there are drones from companies like DJI or Skydio that have very advanced visual SLAM systems, but then also other devices that you might not think of as robots. So things like AR and VR headsets that track their position now using visual SLAM, or there are SLAM systems that even run in mobile phones, and there are applications like you can scan the 3D shape of a room, for instance, just using your smartphone. So those are amazing products, and it's still kind of remarkable to me that you can actually buy those, but I still think this is just the beginning of where we're going with this whole technology. So one of the things that I've been saying in recent years is that I think SLAM is evolving into something much more general and more important. And I've been using the term spatial AI, which in my mind is not something different from SLAM. It's in my mind what SLAM was always trying to be, a general sort of spatial understanding of a scene that enables intelligent action. And we can think of how that research has progressed and will continue to progress in terms of some sort of progress through layers, where the first layer is really the main thing that's in those products you can already buy, robust localization. So where am I? But the layers that build up on top of that will be things like dense mapping. So how can I really build a rich 3D understanding of the scene around me? And then on top of that, semantic understanding. So how can we actually not just have a geometrical representation, but actually have knowledge of all of the objects in the scene and what they actually are. And I think that eventually that will take us to maybe amazing products. So imagine a robot, for instance, that could tidy up your kitchen. Or, these are really, really difficult things. So that product does not exist yet because no one knows how to make it, because it needs kind of perception and scene understanding and then manipulation and all those other things that we don't know how to do yet. So I've got a vision that we're going to be working in this area for many years yet. There are these current products we can get. There are research prototypes that are taking us a little bit across this big gap. And then maybe eventually we get to full spatial AI and this full capability. So how might we actually get there? What are some of the challenges? And I've been thinking about that a lot. Some of my general thoughts, if you're interested, are in this paper called Future Mapping, the computational structure of spatial AI systems. So this is a kind of white paper that I published a few years ago, and it has some kind of hypotheses. One of them is that I think robots that can be really generally capable in spaces and do something like tidying a kitchen, I think they need to build some sort of representation of that scene, which might be kind of close to 3D geometry. So I'm not necessarily saying they need a precise millimeter perfect map of everything, but I think something like a coherent geometry representation will be important for that. And I think there's a generality to what that representation is and what it might enable across quite different types of products. So just to show you very briefly some of this kind of progress through those layers that I talked about. So this was early visual SLAM system. So this was in fact the system called MonoSLAM that I worked on, which at the time was a big breakthrough in terms of real-time monocular SLAM. So here we've just got a singlest hardware setup possible. It's a camera connected to a computer with nothing else. We move it around through this space. We detect and track these point landmarks in the scene. And if I just skip forward a bit, this is essentially the output. So this is the real-time estimate of the motion of the camera and a real-time estimate of the position of these landmark points in the scene. So that's pretty similar to the sort of technology that's in some of the products I showed. This is a more recent system, which is now doing what we call dense SLAM. So this is turning to the side of the problem of, can we actually build in real time a rich geometric representation of a scene? So this is still a SLAM system. We're building this representation and we're tracking against it to estimate the motion of the camera. But it's now not a sparse map of landmarks. It's this dense and detailed map of a scene. But this is still geometry and only geometry. There's no kind of meaning in this. So, what we and others have been working on a lot recently is SLAM systems that actually might start to understand objects in a scene. So just to show you a quick demo of a system called Node SLAM that we built recently. So this actually tries to reconstruct a scene at the level of objects. So it has prior knowledge of certain types of objects it expects to be present in the scene. So here we've got these kind of tabletop objects of bowls and cups and bottles and cans, I think is the other one. And as the camera moves through the scene, it's trying to detect instances of objects like that. And then it's trying to estimate both the pose and the shape of all of those objects. And then essentially those objects become the landmarks in a SLAM like map. So this is a kind of object level SLAM system. And we can actually do pretty useful things with that, such as get a robot to scan a scene like this, map the objects in it, and then have precise enough knowledge of their pose and shape in order to, for instance, pick up all the bowls here and stack them in order. So this is some of the work we do in my Dyson funded lab, where we're very interested in home robotics type of applications. But yeah, so this is the point I really wanted to get to. So we've been achieving this increasing capability in SLAM, but part of that has just been by throwing more and more kind of computation at the problem. And so this is just a rough picture of the kind of computation graph of something like one of these dense semantic object level SLAM systems. It's a very, very complicated system. It uses a lot of computing, a lot of power. So what I've really been interested in is how can we attack that? How can we do better? Because eventually I think we want to get to really high performance spatial AI, but with really kind of low usage of processors and power and sensors and that kind of thing. So how do we attack this? So there's one line of attack which is about representation. So can we do better in terms of how we actually represent the world? And I think the kind of object-based SLAM is a bit of a step in that direction. The other big thing I've been interested in, and really the work that has led me onto the thing I'm talking about today, is thinking about hardware. So when I say hardware, I mean the new sensors and processing technology in particular that are arriving, that are available for us to use in AI, in vision, in robotics. Because I really strongly think that we're at the beginning of a big explosion here. We've been doing things like SLAM using cameras and processors that weren't designed for our applications. They were designed for games and things like that, graphics. There's hardware now arriving, which will be directly designed for us, I think, and what we want to do with it. So, I got very interested in that. I was involved in a collaboration project with universities of Manchester and Edinburgh in particular, thinking about how SLAM algorithms run on different sorts of processors, anything from a big desktop system down to a tiny embedded board. And, remember, we're interested in algorithms that currently we need this sort of resource to use, but we'd really love to run them on this sort of resource. So that really made me think about, the relationship between processing and algorithms. So what sort of processing resource, how parallel it is, and then what sort of algorithms that might allow you to run. And I got particularly interested in this new sort of chip that's come along recently called a graph processor. So this is a picture from GraphCore, which is a company in Bristol that has this new sort of processor called an IPU, an intelligence processing unit. So it's a massively parallel chip, but it's different from a GPU. So it's got thousands of cores on a single chip, but those cores don't all need to be doing the same thing at the same time. They can have very, very general, parallelism. They can all be doing different things. And then it has this very kind of high performance all-to-all interconnect structure. So all these different cores can make some bit of computing, and then they can pass messages between them in quite a general graph-like way to do computations that are of interest. So I really think, this view that processing gets more parallel, but also there's more sort of co-location of processing and the memory that you store. So rather than having memory here and processor here, I think that the general direction will be to much more kind of intermingling between processing and storage and kind of graph-like communication and message passing. So this is what I think was interesting. And so I started to think very strongly about the graph-like structures in SLAM and spatial AI problems. So if we can identify these graphs, we can then design algorithms which we might be able to run really efficiently on these kind of new chips. And that led me in particular to a particular family of algorithms of belief propagation, which of course, belief propagation is a well-known thing. We certainly haven't invented it, but it's a sort of type of algorithm that I think has fallen a bit into disregard and not being used very much. And I think that's because it's a sort of algorithm that doesn't necessarily make much sense on a CPU. I think when you're thinking about this sort of distributed computation, though, it really comes back. So when we're talking about, SLAM problems and doing them properly, what we always do is go back to the probabilistic definition of the inference problem that we're interested in. And in general, we use this factor graph representation as our way of specifying, the structure of a probabilistic problem. So here, for instance, are some example factor graphs. So you can run belief propagation to do inference on factor graphs in a very, very general way. And I've very specifically become interested in Gaussian belief propagation. So this is a subclass of belief propagation where you basically assume that most of the time, most of your distributions are Gaussian. And in my mind, that is hardly a limiting thing at all. You can do almost everything with that, in my opinion, but it's very general, it's very fast, it's very efficient. So we've really followed that. And the first kind of concrete thing we did was to show that you could actually implement this classical computer vision estimation problem of where are the cameras and where are the points that we call bundle adjustment. You can implement that on a graph processor using Gaussian belief propagation, and it runs really fast. So essentially you take your factor graph specifying your estimation problem in computer vision, and you map down, node by node in this factor graph, you map them down onto tiles of a graph processor. And then you run computation by essentially doing local computation and then message passing between the tiles to do inference on this factor graph. So, it looks something like this. We are passing these messages around between the tiles, and we can do all this extremely fast. And we were able to show that, we can actually do bundle adjustment much faster on an IPU than we could on a CPU. So hopefully you're starting to make the link of why maybe these sort of methods might also be relevant to multi-robot localization. I'm going to give you a little bit more of an insight into how Gaussian belief propagation works. So we've written an online article called A Visual Introduction to Gaussian Belief Propagation. So this was led by my PhD student, Joe Ortiz. Let me just show you this briefly to give you a bit more of a feel for how GBP actually works. So this is the article, which anyone can look at. And it's an article in the style of a distill paper, in that it has plenty of kind of interactive elements. So, first of all, a factor graph, it specifies a probabilistic problem like this. So we assume that the joint probability over a set of variables that we're interested in, these x's, is factorizable in this form. So there's some part that might just depend on x, there's some part that might just depend on x2, there's a part that depends on x1 and x3. So that's the factorizability. So when we're specifying problems, usually these circles, the variables, are the things we're interested in estimating. The factors are the pieces of information we have. So for instance, x2 and x1 might be the positions of two cameras, and camera 1 has observed camera 2, for instance. So there's a piece of information which is a measurement of the relative position of those two things, and that would be this factor here. So you build up your whole picture of something like a SLAM problem as a factor graph. So inference means that we want to kind of invert this from knowing what the factors are. That's what directly comes out of our sensors. We want to know what the x's are. So that's called doing inference on the factor graph. And what you eventually want to get to is a marginal estimate of what are the best estimates of the values of x1, x2, and x3, and also what are the probability distributions over those. So that's what doing inference means. And belief propagation says that you can do that by passing messages around the factor graph. And these are the details of all of that, which I won't explain exactly at the moment, but essentially, you just repeatedly pass messages between variables and factors, between factors and variables. So the algorithm of belief propagation is derived, and this is going back, to Pearl's old kind of original work, for a tree-like graph. Factor, it works perfectly. So you just need to send messages all the way from one node out to the leaves, and then send messages all the way back, and it can be shown. So that will definitely give you the right marginals. What we use, and what is very commonly done, is loopy belief propagation. So this means that we have graphs that have cycles in them. When you have cycles, you can't just send messages one way and send them back. You have to send messages that kind of circle around in an iterative way. But it's been shown that this will converge to correct answers in a wide range of useful situations, and specifically Gaussian belief propagation is particularly stable in that regard. So let me just show you something a bit more specific. So these were the first kind of GBP problems that I played around with. Just basically in one dimension, we've got a set of measurements which you might think of height measurements above some kind of surface, which we know are noisy. We're trying to estimate the actual height of that surface on the assumption that we've got these measurements, but also some knowledge that the overall surface is kind of smooth. So we have a factor graph that looks like this, where we've got these measurements which cause these red factors. We've also got smoothness assumptions which cause these gray factors. So this is our factor graph, and then we've got the blue variables that we're trying to estimate. Yeah, so I'm just finding the right part here. So when we solve this with belief propagation, we send messages. So the simple way to do that is to send messages in a sequence. So we're passing messages along the graph from left to right, all the way, and then all the way back from right to left. And because this is a graph that doesn't have any cycles, that works perfectly. We just go one way along and one way back, and we get to this solution. So these blue things are now our estimates of the height of the surface. And actually I can click this. So these green things appear, which is the kind of batch solution to this. It shows that we're getting the right solution. So we can do it in that way, but what's really kind of amazing, so if I just kind of reset this with some new data, we can do in a different sort of message passing. So here we've now got a kind of parallel type of message passing, where every variable passes messages to its neighbors in sequence. And you see that if we iterate for that for a while, we again get to the correct solution. But what's even more kind of remarkable, so here let's just put some kind of random data. We can just do this with a random message passing pattern. So here we're just randomly selecting variables and sending them to pass a message in a random direction to one of their neighbors. And if I click this enough times, again, it will converge to the same thing. I think it's just getting very close there now. You can see that we're pretty much there. You know, if I did this a few more times, we would get there. So that first time I saw that, I thought, well, that's amazing. You know, this is an algorithm that can do global estimation that's convergent, but with a random sort of passing of messages. So here's another kind of example of that, which is now getting closer to this sort of robot localization problem. So this is now a set of points in 2D with relative measurements between them. So we could think of these as robots that are making measurements of each other. And now let's again do random message passing between these things. So it's like there's a relative measurement between every pair represented by these lines joining them. And then we're getting the estimates shown by these kind of circular shapes. So you can see that it's converging. If I do a couple of these synchronous iterations, you'll see that it will converge fast. So a property of loopy belief propagation when we don't have a perfect, when we don't have a tree graph, is that it will converge to the correct means. It may have slightly overconfident covariances, but in my mind, that's not an important thing, because the fact that you can get to the correct means that the relative covariances are correct within this solution of Gaussian belief propagation. So there are some other elements that are really important. So those things I showed you so far were just linear problems. We can also deal with non-linear systems with no problem. And all we have to do is just keep relinearizing our factors. So this is, as is very common in all sorts of non-linear optimization, we can do the same thing. So we can take linear, so for instance, a range bearing measurement between two things is a non-linear function of the positions of those things. We just need to keep relinearizing that into the closest Gaussian, and that works. The other important thing is we can deal with robust factors. So a really important thing in any practical problem is sometimes you get measurements that are just garbage. They're not well represented by a Gaussian distribution, because actually you fairly often get things right out in the tails. You get crazy measurements from real sensors. But we can also cope with that. So we have this method of kind of reweighting measurements to, for instance, simulate something like a Huber kernel that's like a Gaussian that has heavy tails. So if I just show you what that means in this 1D problem, it's this one here. So here, for instance, here's a set of observations that are mostly in a line, but there's a couple of extreme outliers here. If I just run GBP to solve this with our standard, Gaussian model. So here we've got GBP running in the background, solving for the positions of these blue points. These couple of outliers are quite badly affecting the solution. But if I switch here to this Huber kernel, you can see that we can get much more, we can reject basically these bad measurements. So if I have a slightly different set of data, so here's a set of data that looks more or less like a step, where there are two fairly flat regions, and then this kind of sudden change between them. Again, if I solve this using the standard model, we get this kind of blurry thing where it will kind of blur over the edge. Whereas if I switch to Huber, you can see that it does much better at giving us this kind of edge preserving smoothing here. So I'll just briefly show this thing. This is one more thing that we've applied this to, which is you can use this for image processing, and this is very interesting. So exactly the kind of 2D version of the graph I just showed you, which can do edge preserving smoothing, we can apply to a 2D graph like this and use that to remove noise from images. So if I do that with a sort of smooth, so I've got a graph here where we're saying we want to reconstruct an image which is close to this noisy input image, but is also smooth. As I increase the amount of smoothing we apply, if I do that with just a kind of normal Gaussian assumption on the noise, you'll see that it can remove the noise, but at the cost of kind of blurring everything out. Whereas if I do that with a Huber kernel, we can remove the noise, but while retaining the smoothness of the background image. So this is edge preserving smoothing using GBP, and this runs wickedly fast. This is using the kind of the GPU on my just on my laptop here to accelerate this, because this is a sort of computation that's well suited to a GPU. And yeah, so go ahead and play with this web page if you want to understand more about GBP in general. There's even a really cool feature here where you can stream images live from your webcam and do real-time denoising of them. So if I turn this up, you can see that I can ultimately get this extreme smoothing, where it will kind of smooth my face away. So yeah, that's just running in the browser. Okay, so I've given you hopefully a good general flavor now of Gaussian belief propagation. So let's now come back and talk about this multi-robot problem that I told you about at the start. So how are we going to use this now for multi-robot localization? So we've shown that we can take a factor graph and we can solve it in GBP, and we can solve it with this parallel message passing style. So this is really, in this slide here, the core idea of what we call robot web, which is how we can use this for multi-robot localization. So what we do is we think about the full factor graph for a multi-robot problem. So here we're assuming, in this little example, we've got 3 robots, green, blue, and red. Each one of those has been moving through the world. So we've got, for each of these, 6 different time steps shown. So these big circles are pose variables for each of these robots at particular points in time. We assume that we have 2 types of measurements here. We have odometry measurements. So these are these black factors here that join consecutive poses. So the robot might have wheel odometry, it might have an inertial sensor or something estimating its relative motion. And then the robots make measurements of each other. So these factors that join poses from different robots are inter-robot measurements. So those might be robot 1 measuring robot 2, or there might be robot 2 measuring robot 1. And in fact, we differentiate between those 2 things. So the red factors here are the factors that robot 2 has made. The green factors are the factors that robot 1 has made. So that's just the full factor graph. You could define that factor graph, you could upload it to a server, you could solve it with whatever factor graph solver that you want. We want to solve it in a distributed way between all of these devices with message passing. So the simple thing that we do is we basically draw a dotted line around the parts of the factor graph that each of the robots owns. So basically, robot 1 owns all of its pose variables, all of its odometry variables, and then it owns the factors relating to its own sensors and measurements that it has made. So these are the measurements from robot 1's sensors. And robot 2 owns all of the measurements that it has made with its sensors and all of its pose variables. So when we do message passing around this graph, all of the message passing within one robot's dotted line is no problem. You know, that's just done on that robot's own processor. But then the messages that it needs to send between across to another robot, we have a kind of web-like interface for that. So because of this fantastic property that you know, optimization in GBP can be asynchronous, it doesn't really matter what order you send the messages in, as shown by that kind of random clicking I was doing earlier. All that we have to do is each robot looks at its dotted line and basically presents all of the latest outgoing messages from all of these. So it will have a latest outgoing message that it needs to send on this line, on this line, on this line, on this line. It just kind of presents all of that information on something like a web page. So the robots are now just, whenever they can, connecting to each other's web pages, reading the latest outgoing messages. So, you know, robot 2 will connect to robot 1's web page, and it will say, are there any new messages for me? And so, yeah, if robot 1 has done some updates, there should be a new message on this edge, and on this edge that are of interest to robot 2. So it just needs to copy those across. So this is just a little visualization of what that web page might look like. So there's a list of, you know, these are the factors and variables that for which I have a new message for you. And these are small things, these messages. So a typical message in GBP is like a small matrix. So something like a 3x3, or, you know, depends on the dimensionality of the problem. But these are small matrices. So they just need to download a small kind of table of numbers from each other. So via this ad hoc communication, that the whole thing can converge. And I think for me, in the design of this is really important, because we're interested in scalability here. We would eventually like this to run for, you know, hundreds or thousands of devices. So all communication between the devices is via this simple web-like protocol. They don't really need to know anything about each other. They don't need to, you know, robot 2 doesn't need to know how robot 1's sensors work, for instance, because the sensor model is held, you know, within robot 1. The details of this factor are all held within robot 1. So it's this very, very sort of simple and I think very scalable API-like interface. So there's something that does make it somewhat more complicated, but again, we think there's a good solution. So when we have variables that represent things like rotations, so something like a 2D or a 3D rotation, which we represent with groups of, you know, SE2 and SE3 rotation matrices and that kind of thing, we do need to do that properly here. So we've come up with a way of dealing with over-parameterized variables, which uses Lie group theory. And the basic idea is that every message that involves a Lie group variable, you send the whole kind of group element, and then you send a precision matrix in the tangent space of that group element. So again, you're sending small messages around, but you have to be careful about how you use them. So this picture is from an excellent tutorial on Lie groups, which we spent a lot of time reading recently from Joanne Sola et al., which I highly recommend. So let's go back to this demo then, and I'll show you some of the things that this can do. And I should say that this demo is largely thanks to Riku Morai, who's here today, who's a PhD student working in our group. And we will be publishing a paper about this hopefully very soon. Let me just go back and show you this. Okay, so there are several aspects I can show you in this demo. Let's do this one first. So here we've got a scenario where there's, I think, about 30 robots here. And they're all trying to follow circular paths of different radius. So I should say that the planning here is just something very, very simple. So we're talking here about estimation and the robots knowing where they are. If they know where they are, then we can tell them to follow a known path. So each of them is trying to follow a circle, which works if it knows where it is, but doesn't work if it doesn't know where it is. So let's first just run this. So if I just start running this, the robots are all starting to move in circles, and the red lines are showing the measurements between them. So I'm just going to make a couple of changes here. First of all, there are some things I can change. So how many iterations of GBP do we do on each movement step of the robots? That's the thing that I'm changing here. This window is something that we're doing here. So in this current method, to avoid the fact graph just getting bigger and bigger and bigger, we're currently keeping a time window. So I think this is a problem we need to come back and think about more generally in the future. But we're only retaining states and measurements over some window of time in the past. And the other thing is we have some fixed beacons in the scene here. So we have kind of 4 fixed landmarks, which the robots know the position of in the corners of the scene here. So lots of these robots in the center, so there's a limited range of their sensors. They never actually see the landmarks in the corner. They only ever see the other robots. If I turn off this, so turn off the factor display, what you're still seeing is the black lines flashing around. And this is basically the communication pattern. So on every step, each robot at the moment is connecting to one other robot and reading its latest outgoing messages. And it's doing that in a pretty random pattern, which is biased towards reading from robots that are nearby. If I turn that off, it'll become a bit cleaner looking. So now we're just seeing the estimated motions of the robots. And remember that for each of these, there's a ground truth robot and an estimated robot, and they're very much overlaid each other. If I just pause this for a second, I can show you here the kind of the history to show that all the robots have followed a very nice circular trajectory. So again, for comparison, let's just try for a second turning the sensor off. So if I set this to 0, basically the robots will not be using their sensors, and you'll see that they're just using odometry now, and they will basically gradually drift away. So if I again just pause for a second and show you this. So these are what the kind of trajectories look like when we aren't using this GBP and sensing. Okay, I'll show you something a little bit different. So this is another very nice property of this, is it can be very, very dynamic. There's nothing that defines the number of robots in this system in advance, and we can change that dynamically. So here we're going to start with just one robot. It's moving around, and there are 5 known landmarks in the scene. So we can see these kind of properties here that it will, while it's not making any measurements, I wasn't showing the factors. Okay. So here you can see it, making measurements of these fixed landmarks when it's close enough to them. Those will constrain its pose quite nicely. When it moves further away from the landmarks, it's not getting any measurements, and its pose will gradually drift, and you'll see it diverge from the ground truth. Now, what we can do is dynamically add more robots into the scene. So if I click drop robot a few times, each time I do this, we're dropping a new robot in the scene. So the place that you see it drop is where the robot actually is, but we don't know that in advance. So all the robots are initialized, their estimates are initialized basically in the center. So it doesn't know where they are in advance, but they gradually initialize themselves. So you see that these robots, as the moving robot gets close to them and makes observations of them, they eventually get a good enough estimate. So we've set it up so the robots don't start moving until they've got a good estimate of their positions, and then they start moving. And now I think you can really see what we're talking about when we use a word like robot web. We've got this kind of web of localization, which is highly dynamic. So there's one robot here that's, I think it's only just finally localized itself now. But, whereas the original robot, when it moved up into the top left, it really didn't know where it was because it's far from any landmarks. Now, as long as there are some other robots nearby, it can have a good estimate even when it's right out in that region. So we can drop even more in there. So again, let me just show you the kind of extreme robustness of this. So at the moment with this noise percent, so I think that this means a fraction of 1% of all measurements are complete garbage. So there's Gaussian noise on all measurements, but 1% of measurements are complete garbage. If we set that to something actually quite a lot higher here, let's try, for instance, 30%. So this means 30% of measurements are just complete nonsense. But even so, because we're using this robust kernel, we're able to really reject those. So the red lines are the successful measurements that we've kind of accepted. The blue ones are the ones we've rejected because they're far off in the heavy tails of this robust function. So this is very, very robust, even when we've got a lot of garbage measurements. So the last thing I'll show you just towards scalability. So now let's try with 100 robots here. Let's run this. So clearly it's running slower. We're simulating this on the CPU. So of course, if we were running this properly in parallel with all the processing on real robots, it should be much better. But let's just change a couple of things here that should make it faster. So let's do a few less iterations. Let's reduce this window. And then the other thing is probably just reduce the range of the sensor. So rather than 30, let's change that to 10. So now the robots are only making quite local measurements, and we're getting pretty sort of acceptable speed here. Let's just visualize the graph. So here, now you'll see that the robots are only making these very kind of local observations of other robots. The graph sometimes even becomes sort of temporarily disconnected, but none of that matters. This is just a completely general algorithm that can cope with all of these different situations. And I would say most of the robots are, pretty well localized most of the time here. Okay, so I'm going to just go back and finish the slides. We're nearly at the end. Yeah, so there's plenty of further work to do here. So I've shown you this kind of 2D setting. We're pretty keen to try 3D. We don't see why it shouldn't work, and for instance, have both 2D and 3D robots on the ground and drones, for instance. And there's other things we could consider, like auto calibration of sensors of the robots. Long-term operation is pretty interesting. So we've taken a kind of simple approach to that at the moment with using a time window, but in general, we might not be able to do that. I think if there aren't known beacons in the scene, it might not work so well. So we might need to think of something smarter there. Most obviously, taking these complicated big graphs and I think trying to simplify them down into something more abstract. When we actually come to hopefully try and implement this in the real world, what will be the right communication technology to use? In my mind, I've always been thinking a bit like the web. Each robot has a web server, it has Wi-Fi, other robots will log on and read their messages, but maybe we can do much better. Maybe we could use Bluetooth or something, or there's even amazing possibilities where each robot could actually maybe display, it could be carrying a monitor around on top of it, actually displaying this web page, and other robots could just read that with a camera. I mean, that would work. Or maybe we can display everything that should be on that web page in a much more efficient way with like a QR tag or something like that. And then I think a lot of the other issues that are probably of interest in any mobile, multi-robot system. So security. So what if some of these robots are not kind of playing fair? What if they're sending messages that aren't true? I think we can definitely detect robots that are just sending random messages. That's quite easy. The robust methods will just reject that. So if a sensor is broken or something, I think it's not much of a problem. But if a robot was deliberately trying to cheat, I don't know quite how we would cope with that. Privacy is an interesting one. So here I'm thinking, specifically about the privacy of the devices. So maybe in this future where many different companies will make different interfacing products, they might not want to reveal everything about how their product works to everyone else. I think a certain amount of that is built into this system, in that the information about the sensor can still be held internally within the robots. They don't need to reveal everything there. But yeah, is there more to do there? So I've only talked about localization in that these robots are not trying to make a map at the moment, but obviously my background in SLAM means I'm very interested in what if these robots actually wanted to collaborate to build a map of static structure in the scene. We've got some kind of early ideas there, but I think that's a lot more complicated, because basically you'll have factors in the graph, for instance, the position of a landmark that ideally everyone would want to have a copy of where that landmark is. So maybe you need to have multiple copies of the map held in a distributed way, and then the right ways of synchronizing them, which would be okay for a small maps, I think, but probably not for huge maps, where maybe eventually you'd like to share the storage of a big map. And then the other big thing is planning. And in fact, this is something we're already working on. Another one of my students here, Alok, is looking at this side of it. People have shown that you can solve planning problems by factor graph inference. I don't see why we shouldn't do that in a distributed way as well, with very similar methods to this. So that's very much ongoing work. Okay, so just to conclude, so just to returning, what are the long-term prospects of this or other methods? Are we going to have this spatial AI future where there are many smart devices interacting with each other? There's been a lot of talk in the last week or two about things like the metaverse. Companies like Facebook are making massive moves towards a future where they think that people will be carrying smart devices, people will be interoperating with a big shared experience of AR, for instance. And a lot of this discussion, would that be owned by one company, or would it be somehow distributed and a more open protocol? I think there are pros and cons of both. I mean, of course, as this scales, something like a decentralized robot swarm is actually, in some senses, quite a terrifying prospect if it isn't centrally controlled. On the other hand, something that is centrally controlled probably has its own other, things to worry about. Who's controlling it, and do they have good motives? So I'm just saying, I think we should all be part of this conversation about ethics related to all of this. So that I think that if an open protocol that we define for this kind of web-like communication might actually be a really good thing in terms of building trust, and multiple companies could make products that could interoperate with each other. Okay, so just to conclude with mentioning my affiliations. So I'm leading the Dyson Robotics Lab at Imperial College. So this is an academic research lab, postdocs and PhD students, funded by Dyson, mainly focused on research in perception for home robotics. So we're doing SLAM, scene understanding and manipulation. And then I'm also co-founder of a London-based startup called SlamCore, and we develop and sell applied spatial AI solutions. So I'll finish there. Thanks very much.
All right. Thank you very much for a very inspiring talk. And let me just ask one quick question from my side. So I'm kind of interested in implications of computational efficiency with this factor-based approach, because I think factor graph approach, because I think I'm not really sure whether this is the right way to think about it, or is there anything you want to add from this point of view?
Sorry, what was the
question? Computational efficiency, like, is there anything that you can talk about in terms of efficiency?
I mean, it's very efficient. That's the main the main point, because it's entirely distributed. Yeah, it's I can't think of a more efficient way to do it.
Right. So that's actually one of the biggest impacts.
Yeah. So being able to take advantage of the whole sort of distributed web of computation, that's and avoid, we're never having to do anything more than invert a small tiny matrix.
Right.
Most alternative solutions would have you copying all of that data over to somewhere, building huge matrices, inverting and solving them. Most factor graph solvers are are that basically,
Right.
and you need a big CPU to.
So you're outsourcing all this.
Yeah, so I'm really imagining, each of these little robots, it doesn't need much computation, it's a Raspberry Pi or something much smaller,
That's right, yes.
or something tiny, yeah.
Excellent. So yeah, there's some question from the floor. So Roderick, I think there's a microphone coming along, or maybe I just hand it over.
Thanks very much, Andy. Very inspiring talk. I've seen, so I'm very interested about these multiple robots moving around and localizing each other. You have shown one video where they start with an initial estimate and you show that these estimates don't drift off. You have also shown a video where they'd have no prior knowledge, but then you had only one robot moving at the beginning, and then after a while, everyone started moving. So I'm interested in, could there be situations where it's of advantage for all of the robots to move from the very beginning to speed things up? And I'm thinking of, for example, like the kilobot systems, they have so terrible odometry that perhaps in some situations it's so unreliable, the odometry, that it's better to have multiple moving. And also, if you take the collisions between robots into account, if you have n square possible collisions,
interesting. Yeah.
you could say two robots cannot be on the same space.
Oh yeah, I'd love to investigate things like that. I mean, to be quite honest with you, this stuff has only come together and started working in the last few weeks, and we haven't really investigated a lot of those things. So yeah, I guess the hardest possible problem where all your robots are moving, none of them know where they are, and they're passing messages, and you hope that they kind of come into full agreement. I guess we haven't been able to show that working yet. I think what I would hope is, little subgroups of them would start to have messages that started to agree with each other. They'd form into little clusters, and then maybe those clusters would start to join together. Can the whole thing actually converge? I would have hope that it might do. But I think any little bit of extra prior information you can put in there helps a lot. So I guess these things that we did, like the robots stay still while they're trying to initialize, I think that's clearly something that just makes it easier. But that could be anything else. Maybe if each robot had a very approximate compass sensor or something like that, again, that would just help a lot. Or what you suggested about bumping, I was immediately, using a bump detection as a sort of measurement. That's actually a very strong observation. I guess if you know the identity of the thing you're bumping into through some tag, that's a really strong piece of information that you could put into this in principle, I think. So yeah, to be honest, when we were doing, I wasn't necessarily thinking that this self-configuring thing would work at all. I'm surprised it works as well as it does. I was assuming, we would basically be starting from pretty good estimates and try and continue that, which is what we do a lot in SLAM, and we would have a completely separate system to somehow do initialization. But I'm kind of surprised that it can at least do quite promising things in initialization. So certainly if there's a decent established web and you add a few more robots in gradually, I think that's very robust.
Okay, so there's another way to post questions and the online participants if you want to. Okay, there's some more questions from the floor. Do you want to?
Thank you. Hello, I have a question regarding the communication. So you said you showed that random communication. Is it just an observation for now that it seems to work with a random communication, or are there proofs for it? And if you communicate via such a web page or something similar as you showed it, if you overwrite the information while it's read, could that pose a problem that you read inconsistent information, or that it's maybe unreadable depending on the format you publish it, so to say?
Yeah, that's a good question. Probably things that we haven't really faced up to yet, because we're still running everything in simulation and assuming that those whole web pages will change in chunks. Yeah, I couldn't say, to be honest, where that might be a problem. Yeah, and the other question was about random communication. I guess we show that at the moment as a almost deliberately worst case, to show that it can still work in that case. But I think if you were more deterministic about the communication pattern, depending on the technology and knowledge, what you're willing to assume about the other devices, then I think a more systematic pattern can give you more efficient information. So for instance, robots could somehow advertise when they think they've got something really new. So I guess when a robot's own internal state has significantly changed, it could sort of, light up and say, connect to me, I've got something really good. And then that could be much more efficient than just the random pattern. Yeah, or do you move to a system that's more of, pushing the messages? I guess we're assuming you'll always be pulling messages, but maybe with an alternative communication technology, the robots would actually push.
Okay, just a quick question.
Thank you. I was wondering if you could elaborate a bit more on the kind of planning problems that you are starting to look at.
Yeah, it's quite early days, but basically any planning problem that you can formulate as a least squares optimization, you can definitely optimize with this sort of method. So I suppose you've got a robot that wants to get from A to B, and you're assuming it's going to follow a set of steps, and you have some sort of smoothness constraint that says, there's a maximum, amount of dynamics it could have between one step and the next. And then there are some other constraints that, for instance, there are some obstacles in the scene that you want to avoid. You can formulate that as a least squares problem on a factor graph, and then you can solve it with this method. But the interesting prospect is you can then solve that jointly for multiple interacting devices. So we actually have been, in our LOPS work, starting to look at things like, maybe multiple, traffic crossing a junction, and they all want to plan in order to pass through each other without having to slow down much. I mean, we don't have much to show on that yet, but those are some of the prospects, I think.
Okay, so I think I'd like to stop here for coffee break. And I would like to thank Andy once again for a very, very inspiring talk. And he's going to be around for, we can have a lot of discussion in the rest of the conference. Right, thank you very much once again. Thank you.